Hello and welcome to Lecture 8 for the graduate course ECE 254B, Parallel Processing. This lecture covers Chapter 8A in the textbook, entitled Search Acceleration Circuits. As a reminder, Chapters 7 and 8 have been expanded in the new version of the textbook under preparation into 4 chapters. Chapter 7, which I covered last time in the last lecture, remains basically intact. Chapter 8 has been split into 8A, 8B, and 8C by introducing a lot of new material, new examples. So Chapter 8A deals with the search acceleration circuits part of the original Chapter 8. Now, searching and sorting basically almost always go together. One reason being that sorting, one of the main reasons that we sort things is to facilitate searching, make searching easier. Okay, that's why these two go together. Now, simple search can be speeded up by using special circuits. And these circuits were, in fact, these special circuits were the first examples of parallel processors ever developed. They were known as associative memories or content addressable memory. And we'll talk about these. And then more complicated searches can be also implemented, but they require a little bit more hardware and also more ingenuity in designing the architecture to do these things. Okay, so let's now proceed with some examples, beginning with a simple special case of searching, which happens in priority queues. So what is a priority queue? As you see in this image, in the lower part of the slide, a priority queue is basically a storage mechanism into which we store keys. So you see that keys are coming in from the left. So 6, 8, 2, 5 are keys that have not yet entered into the priority queue. And other keys have already entered, 4, 1, 9, 7, 3. So one function of the priority queue is to be able to accommodate these keys as they come in. Another function is to provide us with the smallest key that has already arrived into the priority queue. And this is basically when you have things with different priorities, like tasks, for example, that are waiting to be executed. And when you have resources to execute tasks, you want to grab the highest priority task from the queue and execute that. And highest priority is often indicated with the smallest number. So priority 1 is greater than priority 3, which is in turn greater than priority 4, and so on. So I'm interested in designing a hardware circuit that accommodates numbers as they come in. And then anytime that I'm interested, I can go into this priority queue and grab the smallest number that is in there. Of course, if I keep numbers in unsorted order in the priority queue, insertion will be very simple. I can simply put a regular queue or a stack and just put in the next number as it comes in. But the numbers appear in the queue in no particular order. So when I want the smallest number, I have to go in and actually search for it, and that can take linear time. Okay, so unsorted list will have constant time insertion, linear time extraction. If I sort the list, then so that, for example, the number 1 is always at the head of the list, then extraction will be constant time because I know where to look for that smallest number. But insertion will take time because I have to, every time a new number comes in, I have to update my sorting, and that can take linear time again. Okay, so there's a trade-off. I can either do insertion fast or I can do extraction fast. So a natural question is, can both insert and extract operations, which are the main priority queue operations, be performed in constant time, independent of the size of the list? So even if I have 10,000 numbers in the priority queue, I can still insert in constant time, and I can extract in constant. That would be a very good feature to have for large priority queues. Okay, so here is our first attempt at solving this problem. We'll see that it doesn't work, but it gives us an idea how to fix the problem so that it does work. So remember the linear array sorter that we discussed before? Basically, I have a linear array of cells or simple processors, and numbers come in from the left. And as each number comes in, so for example, 4 comes in, this cell is empty. You can view empty cells as holding very large numbers, so infinity. So 4 is compared to infinity. The smaller of the two is kept here, and the larger of the two is sent to the right. Then 1 comes in. 1 is compared to 4. The smaller of the two is kept here, and 4 is pushed to the right. So as numbers come in, the smallest number that we have encountered so far sits in this head cell of the linear array, and therefore we might think that, well, extraction would be easy because I always have the smallest number in this particular place. The problem is, let's say at this point I decide to extract. So some numbers come in, I put them in, but at this point, before the next number comes in, I want to extract the smallest number from the priority queue. Sure, I can extract this 1, but when I extract this 1, a hole is created, an empty space here. And if I immediately decide to extract the next smaller number, that next smaller number, which is 4 at this point, is sitting here. So it's not easily accessible. So I need to do some rearrangement of the contents of the queue so that when I extract something, the smallest value, the other values are rearranged so that the next smallest number now sits here. Okay? And this cannot be done with this architecture because I extract 1 and now 4 is sitting here. Assuming somehow I can get to 4, well, actually 3 is the, if I do extraction at this point, 3 is the next smallest, then 4. Okay, so if I extract at this point, let's say this row, I can extract 1, but then the next smallest number is here, and the next smallest after that is over here. Okay, so they can be arbitrarily deep in this structure so that I can't get access to them in constant time. So what's the cure for this problem? It turns out we can, by just allowing inputs to come in on alternate cycles rather than on every cycle. So on odd numbered cycles, for example, cycle 1, cycle 3, cycle 5, we can accept new inputs. Even numbered cycles 2, 4 is an idle time that allows the array to reorganize itself so that it's ready to satisfy the next request that comes in. So let's take this example. So at this point, a bunch of numbers have come in and they're at various places in the queue. This number 3 has not yet been inserted. suddenly we decide to extract. Instead of admit the next number, we stop the flow of incoming numbers and extract this one. So we look here, extract it. Now this cell is empty. During the idle cycle, after this, because on every other cycle we don't do anything, just allow the array to reorganize itself, any cell that notices an empty cell to its left will shift its value into that cell. So 4 will go here, and in the next, as I extract 1, 4 will move here, and in the next cycle 7 will move here because this cell is now empty. And this is just enough for me to always have the smallest number here. So the next smallest number is 4. I extract it, and then magically the next smallest number, 7, moves into here. So these alternate idle cycles provide enough time for the array to reorganize itself so that the smallest number is always at the head. No matter how many numbers I've input, this is always doable. And then once I've done 3 extractions, I can resume perhaps insertions, and the insertions would work as before. The 3 replaces 9, and 9 is pushed to the right, and so on. So this is called a systolic priority queue because the clock cycle, or the rate at which I can input data and extract data, is independent of the size of the queue. No matter how long the queue, I can always do, of course, I'm wasting half of the clock cycles, but still it's constant time. On every other cycle, I can insert or extract regardless of the size of the queue. Okay, of course, I could have designed this queue in the following way. If it wasn't too big, whenever I extract something like this one, I could broadcast a signal to all these cells and say, I have extracted something, therefore every cell please move your contents to the left. Okay, that's also a valid design, but it's not systolic because that line that broadcasts the signal to every cell, first of all, it's long, so its latency will be proportional to the length of the array. And also the loading on that line, if it's connected to every cell here, would be unacceptable if the number of cells is very large. Okay, so that's why we are interested in systolic priority queues, because now all the connections or the wires are short, and furthermore the operations of interest can be done in constant time, independent of the size of the array. Okay, this is another data structure that does the same, performs the same functions, but also more. Okay, so this one not only gives us the smallest value in the priority queue, but also the largest value if we are interested in getting the largest value, and also the median value. So it has 3 functions rolled into one. We have stored a bunch of data here. I'll show you in a minute how they are stored. Anytime I'm interested, I can insert values into this queue. Insertion takes constant time. And I can extract at my option the smallest value, the largest value, or the median value. So the same structure serves 3 purposes. So it's a very interesting data structure. So S is the smallest, M is the median, L is the largest. So the smallest value overall is sitting here, the largest value overall is sitting here, and the median value of the entire list is sitting here. Then the left subtree contains values that are between S and M, and the right subtree contains values that are between M and L. And if the 2 subtrees are balanced, they have the same number of elements, then obviously this thing sitting in the middle is the median. Okay? Of course, we cannot balance the tree if the total number of elements is odd, in which case we sort of agree if the total number of elements in the two subtrees is odd, we put one fewer element in the left subtree compared with the right subtree. So for example, if you have 20 elements that need to go into this two subtree, so we have 23 elements overall. There are 3 elements at the root and 20 that need to go into the subtrees. Oh, sorry, 20 overall. 3 go in the root, and I'm left with 17 that need to go into the two subtrees. Now 17 is odd, so I put 8 of them on the left and 9 of them on the right. So if there's an imbalance per convention, per agreement, we put one fewer element in the left subtree than in the right subtree. If there's balance, then the two subtrees are exactly of equal size. Now let's take this 8 element subtree on the left. The 8 element subtree will have 3 elements at its root, and then 2 elements on the left, and 3 elements of the right. So this structure, this convention, is applied recursively to the subtrees. So here I've shown a list with, let's say, 42 or 43 elements. If there are 43 elements, 3 are sitting at the root, 20 on the left and 20 on the right. If I have 42 elements, again 3 are sitting at the root, 19 will be on the left and 20 on the right by convention. So all the elements, so 5 is the smallest element overall, 176 is the largest, and 87 is the median. Okay? All the elements in the left subtree are between 5 and 87 inclusive. So they can equal to 5, they can equal to 87. There are in this interval 5 to 87. All the elements in the right subtree are in the interval 87 to 176. Okay, so let's see how we insert and extract stuff from here. Suppose I want to insert 2. So insert 2. There's an input to the root. The root compares 2 to the smallest element overall. And notices that 2 is smaller than 5. So it replaces 5 with 2, the new number that came in, and pushes 5 into this tree. Okay, now the smallest element is 2, and elements in this subtree will be in the range of 2 to 87. Now, if this subtree has one fewer elements than the one on the right, there's a tag here that says when we have complete balance and when this subtree is smaller. If this subtree is smaller, and pushing 5 into it makes it of equal size to this one, we don't need to do anything else. So the 5 will go here. It's compared against this S. If it's smaller, it will replace this S, and the S is pushed. Okay? But we don't need to wait for all these, basically the propagation down the tree to complete. As soon as 5 is pushed into this tree and goes here, this data structure is free to do the next operation, either insert or extract, because things basically flow in a pipeline manner. It will go from this level to this level to this level. We don't have to wait for that to complete, because if we ever need this node again, that it's already done with the function of inserting 5, and therefore it's available for the next operation. So on every clock cycle, this one can accept a new number, possibly pushing a number here. And then when that number is pushed, on the next clock cycle, this one will do the same thing. On the next clock cycle, this one, and so on. Of course, if that number that comes in is, let's say, between M and L, then it will be pushed in this direction. So that's the simple case. When I don't have balance and this number that went here creates balance, and I'm done. Now suppose I have balance. There are 20 elements here, 20 elements here. 2 comes in and 5 is pushed here. Now I will have 21 elements here and 20 elements here, which violates the convention that I said, if there is a lack of balance, then the left subtree should be smaller. Okay, that can be easily fixed by basically doing something to these 3 elements. So this side has one more element. So I extract L from it and put it here and push M down to the right. When I extract L, that creates another chain reaction because this place is now empty. Then this L will move up there and so on. Again, I don't need to wait for this to complete before proceeding to the next step. By the way, the order of elements in this tree is like this: smallest, second smallest, third smallest, fourth, this way, and it gets larger, and I go through this path. So this is the order of elements stored in this tree. Then I get to the middle element, and then I go to the larger elements on this side. It's sort of like a chain. And finally, I get to the largest element. Okay, if I want to do extract min, here it is, I extract it. Because I extract S, I need to sort of replenish by pulling this up. So this cell basically signals to this one that I need your smallest element. And when this is pushed up there, again, a hole is created here. So again, there's a chain reaction that we don't need to wait for it to complete. Now, if this side has 20 elements and I remove this S to fill this space here, then it now has 19 and I'm still okay. If it had 19 and I pulled one element, it now has 18, and this side has 20, then I have to rebalance, and that rebalancing is done by pulling this S up to replace M and pushing M down into the left subtree. Okay, if I insert 20, 20 is between these two, so it's just pushed into here. Again, rebalancing may be needed. If I want to insert 127, 127 is between these two, I would insert it here. If I originally had balance, inserting one here is still okay. If this side was smaller than this side, then pushing this will make this 2 larger than this. I need to rebalance. And finally, if I insert 195, which is larger than this one, it replaces this, and this element is pushed. So whenever I push something to the left subtree or to the right subtree, if balance conditions are violated, I will have to rebalance. But rebalancing always involves just local operations. Either pull L up and push M down to the other side, or push this S up and pull this up and push M to the left side. And once this local operations between adjacent cells is complete, the rest will take care of itself, and I don't need to wait for it to complete. Okay, we talked about searching on PRAM. Let me just briefly review what we did there. We said if you have a list of n elements and you have, let's say, 2 processors, you allow those 2 processors to probe elements that are 1/3 down the list and 2/3 down the list. Either one of these processors find the element that you're looking for, in which case we are done, or the more likely case, neither one finds the element, but they establish the element to be in this third of the list, or in the middle third of the list, or in the last third of the list. Okay, more generally, if you have P processors, you divide the list into P+1 segments, and therefore the number of probes, in the worst case, will be log base P+1 of n+1, which in the special case of one processor P equal to 1 will be log base 2 of n+1, which is binary search that we already know about. Okay, so log in base P+1 of n+1 is log base 2 of n+1 divided by log base 2 of P+1. This is the binary search time with one processor. So this factor here is the speed up, how much faster we are doing this compared with binary search. So it's a logarithmic speed up, which is not very impressive. So a single search in the sorted list can't be significantly speeded up through parallel processing. However, if we have dynamic data, and dynamic data basically changes so that the sorted order can get messed up, we have to resort, then we can do that resorting much faster with multiple processors, and therefore the advantage will be more. Or if we have batch searching, and we'll talk about that later, multiple lookups done at the same time can be speeded up through pipelining, and we'll see an example of that in a few minutes. So this kind of operations that we define in a priority queue in a queue, not necessarily priority queue, are generalized into what we call dictionary operations. Like dictionary lookup is basically a search, okay? So we might search for Y, the key Y, find a record with key Y, return its associated data. So in a dictionary, we look for a word, and then the associated data is the meanings associated with that word. Okay, we also want to be able to insert a record with key Y and data Z, put a new word in the dictionary along with its meaning. We also want to be able to delete an element from the dictionary when it becomes obsolete, no longer needed. These are the three basic dictionary operations are search, insert, and delete. In addition, depending on application, we may want to incorporate some of these other operations. Find min, for example, this was needed in the priority queue. Find the smallest element. And extract min is basically not just find it, but also extract it, remove it from the queue. Find max, extract max. Find median, extract median. These are things that we discussed on the previous slide. And we might also want to find the best match, the closest match. So we are looking for something, and that something may not be in the list we are searching, in which case we are interested in finding the best match. So in terms of dictionary, we may have misspelled the word. So the word itself that we have is not in the dictionary, but the best match is perhaps what we are looking for and should be retrieved. Find next, basically for numerical values. So I'm looking for the number 25 in this list, but 25 may not be in the list, in which case the next higher, for example, 27 may be the next higher. I want to retrieve that. So something close to what I'm looking for that is a little bit larger. And previous is just the opposite, something that is close but a little bit smaller than what I'm looking for. Okay, now in the early 1980s, this dictionary machine architecture was proposed. It's not a very practical proposal, but it's very interesting from a theoretical standpoint, and we can convert it into a practical design with some modifications in it. So this is a tree-structured dictionary machine. It's basically two trees, the circle tree and the triangular note tree, attached to each other, connected to each other back to back. So the leaves are shared between these two trees. Now records to be searched are stored in the leaves. So in this small example, I've shown only 8 records stored. Okay, so when I want to search for something, I insert the search instruction into this root, and that search instruction is broadcast down the tree until it gets to all the leaves that store records. So for example, I say search for the number 35. So this one notifies these two, search for 35. These two notify these four, search for 35. And these four notify the leaves, search for 35. So the leaves compare the incoming number or the incoming key more generally to what they store, and then they respond. Okay, in the case of simple search, say yes, I have that record, or no, I don't have that record. Then these responses are combined in these triangular nodes. So this one says yes, this one says no. So combination will be yes, along with identification that it was found here. And then yes and no, this will be yes. Eventually you find out that yes, the key was found and it was in this particular cell. Now, we can pipeline multiple searches. As soon as search 1 goes to this level, we can accept a new search at this level. I'm envisaging this as being clocked. So on one clock cycle, the search instruction comes here. Then it's moved to these two nodes, and the second search instruction comes here. In the next cycle, the search that was here moves to this level. The second search moves to this level, and the third search can be accepted. So this is basically an example of batch searching. We are doing a lot of searches. Now the first search takes logarithmic time to get through this tree structure. Actually 2 log. If I have n records here, it takes log n minus 1 levels, in this case, let's see, no, sorry, log n levels, 1, 2, 3, for the search instruction to get here, and then 1, 2, 3 for the result to propagate to the output root. So 2 log n clock cycles are needed for that search to complete. However, every subsequent search can be initiated 1 clock cycle after the previous one. So if I have a large number of searches to perform, then ignoring the initial delay through the tree, I will be doing 1 search on every clock cycle, roughly. Okay, if I have a large number. All right, searching therefore is easy. There's a lot of hardware involved. If I have 1,000,000 records, then I have, of course, 1,000,000 cells here, but also roughly 1,000,000 of these circular nodes and roughly 1,000,000 of these triangular nodes. A lot of hardware is involved. But you can envisage that each of these cells, instead of holding just 1 key, maybe it holds 100 keys. Then when the search instruction comes here, then this one searches in its sublist and then notifies its finding in that sublist. So I have fewer cells, fewer circles, fewer triangles. But then now the clock cycle will be longer because the rate at which instruction will be processed will be dictated by how fast each of these can search within its own sublist. That's a bit more practical because we have less hardware, but also slower in terms of speed. Okay, so I can do minimum finding for this. So the search instruction says find minimum. Then these two basically say, here's my value. This one says, here's my value. And the triangular cell says, okay, here's the minimum of those two. And this one says, here's the minimum of these two. So minimum finding and maximum finding is also possible. Median finding cannot be done with this particular architecture. A best match can be found. So the key comes in, this one matches and sort of computes a match degree according to some formula. So this one says, here's my match degree. This one says, here's my match degree. The better of those two is forwarded now. So we can do minimum, maximum, best finding, but not median. So far so good. But what about insertion and deletion? Here's when some complications arise. If you want to insert something into the structure, you assume that there's some room. So for example, these start cells are already occupied. Blank cells are free. Are places where we can insert new records, key value pairs. Okay? So in order to know where these empty spaces are, we associate two counters with each circular cell. One counter says how many spaces there are in the left subtree. So in this case, there's one space, so this counter is 1. And in the right subtree, there are 2 spaces. So these counters basically indicate how much space I have to the right, how much space to the left. When an insertion takes place, I look at these two counters. In this case, both of them are non-zero, so it's my choice which side to direct the insert. Let's say I decide to send it this way. So that counter, which was 1, is now decremented to 0 because eventually this record will occupy this empty space. Again, this one has counters 0 and 1. So this one has no choice but to go to the right. And this one has counters 1 and 0. So it goes here and eventually will be inserted in this location. Now the next insert that comes in will have to go to the right because this counter is already 0. And therefore it will go here. This 2 will be decremented to 1. Here it has no choice but to go to the right. This 2 will be decremented to 1. And here it has a choice of going right or left or right. And so insertion problem is solved by using two counters for each circular cell. And these two counters are updated appropriately as we insert records. Okay? So far, so good. What about delete? So when a delete instruction comes in, says delete a particular record with a given key, that delete instruction is broadcast and then eventually gets to all the cells. Let's say this cell has a record with that key, so it deletes that record. Okay? However, when something is deleted, we need to update these counters. So this now must become 3 because there are 3 empty spaces here. This one must become 1 and this 0 must become 1. How do we do that? Well, the lower subtree basically, when some cell deletes a record, It basically notifies, gives its address that I'm the one who deleted, and this address emerges from here. So we need a second pass through the tree. So whenever a delete occurs, another instruction is inserted into the tree to reclaim that empty space. So an instruction comes here and says, okay, so this cell deleted something, therefore update the counters. We know that this cell is to the right because of its address, so update this 2 to 3. We know the cell is to the left, update this to 1, update this to 1. So a second pass through the tree is needed to update the counters to reclaim the free space for subsequent use. So there's a delay, slight delay between the time when the record is deleted and the time when the space becomes visible through these counters. That small delay usually is not a problem because we often have a lot of empty space here. And if one space is invisible to us for a short while, is not a problem. More importantly, this deletion actually takes 2 cycles. One cycle through the tree to do the actual deletion. And so basically searching and insertion must be paused, must be stopped while this update takes place. So it occupies one cycle of one extra cycle of the machine to update these counters. If deletions are rare, then this may not be a serious performance disadvantage. Okay, so here for the sake of simplicity in describing the machine, I've described it as having 2 trees, the circle tree and the triangle tree. In hardware implementation, actually these 2 trees are merged by folding the machine to get a regular ordinary tree where each node has both the circle function and the triangle function. Okay, so this is basically the common root. The instructions come in here and the results emerge from here. And therefore, all the nodes are similar. They have a circle part and a triangle part with these connections. Now, once we convert this into a tree, then physical hardware implementation can take advantage of what we know about laying out trees on VLSI chips. So this is an example of a large binary tree that is laid out on a square or rectangular chip. The root of the tree is here. The dark orange nodes are the 2 children of the root. The light orange nodes are the 4 children of these 2. And then I've shown just one path. Then this is a child of that node, child of this node, the child of that node, and so on and so forth until we get to the leaves, which are the end point of these. You see there are H patterns. This is known as an H tree layout. Okay, and the primary use of it in VLSI is for clock distribution. So if this is a clock signal, it will be distributed throughout the chip through these paths in such a way that the delay from the input to every one of these endpoints is exactly the same, because the clock signal goes through exactly the same wiring pattern to get here. Okay, so for example, the circuits that are in this area on the chip will be fed by this clock signal. The circuits that are in this adjacent area will be fed by this clock signal. So there will be very little clock skew. Clock signal will get to all areas of the chip almost exactly at the same time. Therefore, we won't have much clock skew, which can generate problems. Okay, so the same idea for laying out clock trees can be used for laying out an arbitrary tree architecture on a two-dimensional chip. Okay, the next topic that I want to discuss is that of associative memories. I mentioned that associative memories represent the oldest parallel processing technology. So let me describe what associative memories. These are sometimes also known as content addressable memories. So AMs, associative memories, or content addressable memories, or CAMs, are the same thing. So here to explain what CAMs or AMs are, this is basically an SRAM, a 6-transistor SRAM, static random access memory cell. Now SRAM is a faster memory technology than DRAM. Therefore, we use it only when high speed is required because it's at least 6 times as expensive as DRAM because a DRAM cell has a single transistor. So the way this works, the 4 transistors in the middle are basically the memory cell that stores a bit, and that bit is D. So both D and D bar are available from this memory cell. Okay. Then when we want to read the contents of a word from an SRAM, we select that word using the word line. So the decoder basically selects this word, says I want to read this word. Okay, when this word is selected, these signals are asserted, and therefore these two switches open, and the value of D stored in this cell appears on this line, and the value of D bar on this line, and these go to the place where the content is detected. So we see whether a 0 or a 1 is stored here, and in different bit positions we read those bits, and that's what gives us a word out of the memory. Okay, I can easily convert this to an associative memory by taking the storage cell, and instead of putting these 2 transistors here, put these 4 transistors. And this allows me to search for a particular content within the cells. Okay, so I may be searching, it's a query. I want to see whether this cell contains 0, for example. If I want to see that this cell contains 0, then this line will be asserted. When this line is asserted, if the cell contains 1, then this line is asserted. Okay, so both of these switches open, and therefore the match line, which is initially set to 1 through pre-charging, will be drained basically through this path, and therefore a mismatch is indicated. So the way this memory operates is that the match line is preset through pre-charge to 1, and as any single mismatch in the various bits will reset that to 0. So if I'm searching for 0 and the cell is 1, or I'm searching for 1 and the cell contains 0, in other words this bit is 1, then this charge takes place and a mismatch is indicated. Okay, so before describing the diagram to the right, let me go to the next slide. This is basically what happened. This is multiple bit positions. So I'm searching for something in this bit position. I'm searching for something in this position. If all of these indicate a match, none of these paths will open, and therefore the match line, which is pre-charged, will stay asserted will stay at 1, and therefore a match indicated. Let's say this word matches the content that we are looking for. So this is also where the name content addressable memory comes from. I don't access this memory by providing an address. In fact, I don't know where each thing is stored. I just query the memory and say, I'm looking for this particular bit pattern, and the words that contain that bit pattern will respond by asserting this match line. And this is basically a memory array. I'll come back to this. So match line for word 0, match line for word 1, and in this case, 2 words have indicated match, 2 words have indicated mismatch, and then some kind of encoder is used to, let's say, the lowest match address will be output. Okay, let me go back now. I'll come back to this. So this is basically a binary CAM or binary AM. This is a ternary or 3-state CAM or AM that has a lot of applications in modern digital circuits. I'll show you some of them later. Here, the memory cell stores not just 0 and 1, but can also store don't care X. So basically, it's 3 valued. Actually, it may be 4 values if we implement it as two flip-flops. Okay? So one particular pattern represents 0, this pattern represents 1, and 0, 0 represents don't care. So if this particular cell is storing don't care, then both of these lines will be 0, and therefore neither of these paths will open, and therefore this particular cell will never mismatch something. Okay, that's the meaning of don't care. If I'm searching for 0, if I'm searching for 1, this cell will match it. Okay, and the rest of the operation is the same as before. Okay, so if I want to search for the pattern 0, 1, don't care 1, and this, let's say here, 0, 1, 1, 0, don't care. Okay, sorry. If I'm searching for 0, 1, 1, 0, 1, let's say, this pattern, 0 matches this 0, 1 matches this 1, 1 matches this 1, 0 matches this 0, and the 1 that I want in the 5th position matches this X, so this one will respond to that query. Okay, and this is basically one of the applications of ternary CAMs when we want to match internet addresses to addresses stored in a table for the purpose of routing. So for example, this entry of the table, so it says, of course this is too small to be an actual routing table, but it says internet addresses that start with 101 should go to this particular destination. Okay, so if this one matches, we know where to send it. Internet addresses that start with 0110, doesn't matter what comes next, should go to this destination, and so on. And these are stored in order from the shortest addresses to the longest addresses. Okay, so if an address matches, let's say this one, but also a shorter address, it's sent, this is more specific. So it will be sent to the address indicated by this longer entry in the table. So in this example, you see search data is 01101. There's a mismatch here. There's a mismatch here in the first bit. match 0, match 1, match 1, match 0. Remember, X matches anything, and match 1. So that's why both of these lines have matched. So this one would indicate that 0, 1 matched, and that 0, 1 in some other table says where to send this particular packet. So the routing decision is made in this way. Because this table is large and packets arrive at a high rate, I want to be able to decide quickly where to send this packet. So this is why I need this parallel searching capability. So these are some of the current CAM applications: packet forwarding, packet classification. So packets have fields that indicate the type of the packet, and sometimes the handling of the packet depends on the category to which it belongs. So we want to quickly classify packets. We can use this kind of CAM. Associative caches, translation look-aside buffer, which is a form of cache, can also be implemented using associative memories. So a TLB typically contains a few tens of entries, not very many, maybe 64 entries. And whenever an address tag is generated, we have to check the TLB to see if the translation associated with that virtual tag has been performed recently, in which case we avoid the slow, lengthy translation process by just reading out from the table the translated physical address. So again, because on every memory access the TLB is consulted, we have to make it fast. Therefore, we need to do parallel searching. And data compression is another example. So a data stream is coming in, and when strings are noticed in the input, we search a table to see if we can replace those long strings with shorter representations to basically compress the data. An example would be replacing the string University of California, Santa Barbara with a shorter string UCSB. So whenever the string University of California, Santa Barbara is detected in the input, okay, we consult an associative memory to see what the corresponding shorthand notation or compressed form is for that particular string. Okay, here I've shown basically how an associative memory is used. So you have two registers. One is comparand, the thing we are comparing to, and a mask that says we are only interested in this part of the comparand. So typically, words of associative memory are very long. They contain not just word, like 32 or 64 bits, but they contain a record, many fields. So I may be searching, for example, if this is a student database, the perm number field, or the birth year field, or some other field. So I mask out the rest of the record, the red part, and say, okay, search for this pattern among all the words. Okay, so when a mask occurs, no searching takes place. Yeah. In this part, searching takes place, and some of these records respond as matching that. Of course, if I'm searching for perm number, the example I indicated, there will be just one matching record. But if this is, say, birth year, then there may be many matching records, and I have to have some way of handling or processing multiple matches. This is basically a brief history of associative memories starting from the 1940s. I learned about associative memories in 1960s when I was doing late 1960s when I was doing my PhD thesis, and so I entered the picture here. Okay, now once we have associative memories, it's just a simple step to extend their capabilities to turn them into associative processors. Now, an associative memory can basically do search operations, search for something, okay? Now, we can extend the capability to many other operations, including arithmetic operations. So basically, there's a control unit, which is basically like a CPU here, comparand register, mask register. So the cells basically respond to the query. Responses are stored here. There is a special unit here that allows us to process single or multiple matches and then direct the control unit to do something. For example, take the matching entries out one at a time and do something to them sequentially. Or you can do, for example, if a few cells match in a numerical field, in parallel you can say increment that numerical field by providing arithmetic capabilities within these cells. So it's a combination of associative memories and parallel processing in terms of arithmetic and logic operations. Okay, now with this associative processor, so associative devices is a term I use to refer to both associative memories and associative processors. Okay, so these associative devices can do exact match, which is what I described in relation to associative memories. They can do inexact match, which is a little bit more complicated. Find numerically or logically proximate values. Membership search, identifying all members of a specified set. Relational search, determining values that are less than or equal, etc. Interval search, marking items that are between or outside given limits. Extrema search, finding the maximum, minimum, and so on. Rank-based search, selecting the kth or k largest smallest element. And finally, ordered retrieval, which is basically repeated max or min finding with elimination, which leads to sorting. So if I find the maximum value very quickly in one cycle of the associative memory, if I can eliminate it at the same time, then the next max finding gives me the next largest element. The next max finding gives me the next largest element. So I basically sort the elements in this memory using repeated max or min finding operations. Now, associative devices can be classified into 4 categories. Now, basically, computer architects are very fond of this type of classification that leads to 4 categories. Remember the Flynn classification, SIMD, MIMD, MISTY, and SISTY. Okay. Then the Johnson classification of shared memory, distributed memory, and so on. That 4 categories. And this one has 4 categories. And there are 2 axes, how the words are handled in parallel or in serial, how the bits within words are handled in parallel or serial, fully parallel associative devices, bit serial associative devices, word serial associative devices, and fully serial. Now this category is not all that useful because if you process the word serially and the bits within word serially, then you basically don't have any parallel processing. But this category is not of interest. Remember the other 4 category classifications also, all of them had 1/4 that was not very useful. So this one is not useful. This is basically what associative memories do. And let me describe these two. So word serial. What does it mean, word serial? It means the words, we have many words, and these words are stored in shift registers. In other words, the first word is stored at the head of these shift registers. So one bit from each word is stored in a shift register together. So this is one word, this is another word, this is another word. So words are shifted into the processing logic one at a time. Processing takes place. So for example, if there's an unordered list stored here, and I'm looking for a particular element, the first word is shifted into here. I compare it to what I'm looking for, then the next word. So once I've seen all these words, I basically conclude whether that word existed, or maybe how many copies of that word existed, and so on. So the question is, if I'm processing words serially, how is this different from a normal sequential processor? In sequential processing, we do the same thing, right? We fetch a word from memory, do whatever needs to be done with that, then go to the next one. The difference is that when I do this on a sequential processor, for example, I write a loop, program loop, that says fetch the next word, do the processing, then the loop has some basically control that says increment the index, compare the index to the maximum so that I know when to exit the loop, and so on. So there's a lot of overhead when I do this using sequential programming. First of all, there is the instruction fetch and decode overhead. Then there are many instructions in a loop, some of which are overhead, basically loop control instructions. And then I have a memory access, which can be pretty slow. Here I'm doing the same thing. I'm basically cycling all the words through this logic, except I'm doing it at hardware speed. There's no decoding involved. There's no memory access involved because shift registers can be very high throughput. So on every nanosecond or fraction of nanosecond clock cycle, a new word can go here, whereas fetching a new word from memory can take a long time. Okay, so this can be viewed as hardware implementation of a program loop. And if the number of words is manageable, is not too large, I can go through all of them rather quickly and complete the processing in a small fraction of the time needed if I had done this using a program loop. Okay, so there's word serial associated devices. Words are handled serially, but bits within the same word are handled in parallel. Okay, now going to the other side, where bits are handled serially, but words are handled in parallel. These are known as bit serial associative devices. This basically corresponds to sort of flipping the memory on its head. Normally, we take a word of memory out and process it. Here, we take a bit slice. A bit slice is basically one bit of every word. We take it out and process it. So because there are many more words than there are bits within words, the amount of parallel processing is much higher, while the hardware complexity remains reasonable because the processing elements dealing with bits, these are basically bit processors. So they're very simple logic devices. They're not, a Pentium or some other kind of processor. They're very simple. And I'll show you an example of this bit serial processing. For this reason, we often call these processing elements rather than processors. Okay, so an example of what these simple processors can do, suppose there are field A within within each word, and field B, and a field S. So I want to take the number in field A, add it to the number in field B, and store the result in field C. How do I do this? Well, I read the next bit of slice A, basically initially the first bit, the 0th bit, into the processing element. Read the next bit of slice B, read the least significant bit of slice B, and carry from the previous slice is in flag C within the processor. Find some bits, store them in bit slice of S. So once I've added those two bit slices, I store the result in another slice. Keep the carries in these flags, and then repeat the process. So if these fields that I'm adding are 16 bits wide, within 16 cycles, I'll be adding all of those 16-bit numbers, and there can be many, many thousands of such words. So in 16 device cycle, associative device cycle, I'm performing thousands or perhaps even millions of additions. So that's where the speed comes. Meanwhile, I'm using very simple processing elements. Okay, this is an old example of an associative processor. The very first important device in this category, Goodyear Staran. It was aimed at air traffic control applications. In air traffic control applications, data from N aircraft that are close to a major airport are stored, and then we have to make sure that these aircrafts do not get too close to each other to avoid collision. Therefore, pairwise, the locations of these aircraft must be compared. So we need order n squared operations. Now with an associative processors, we need order n operations because one aircraft's data can be compared in parallel to the data from all other aircrafts. So this was the intended application of this associative device. And now, if I go here, if each processing element only has access to bits in its own word, then they can never communicate, and therefore not much useful processing can take place, where the result depends on multiple words, because each PE is devoted to just one word. In order to allow these kinds of communications, Staran had this network sitting between memory and processors. So instead of routing memory location 0 to processor 0, memory location 1 to processor 1, it could sort of rearrange them into different patterns. Now these patterns were judged to be important by the designers of this network, where adjacent processors exchange values, or this kind of exchange takes place, or this kind of exchange, and so on. So it makes it more useful by allowing the processors to communicate, exchange values. A distributed array processor is a more recent example of an associative processor. And this is an example of that single bit processor that I mentioned. There's a full adder, so that's basically the ALU of this, a single bit full adder. There are a couple of muxes and 5 single bit registers. Okay, so that's the extent of complexity. 5 single bit registers, a single bit full adder, and 2 4-to-1 muxes. Okay, so when we want to add stuff, typically 2 values come. So this is the carry from the previous stage. Typically, this is a bit, and this is a bit that comes from a neighbor. And the north, east, south, and west neighbor can send a value to this processor. Addition takes place. The carry is stored here. or sometimes it's sent to a neighbor. And the sum basically can be stored back or can be sent to memory. So this is a very simple processor, single bit processor. And an array of such processors is used as shown here. So basically each processor has a Q register, an A register, a C register, a D register, and an S register. S is not shown here, but the Q registers of all the processors forms this plane. So it's a two-dimensional plane. Each bit comes from a processor. Okay, and this is basically the memory. So the processor that say is at this corner has access to bits, these bits of memory in this corner. But the processors can exchange values through these. So this processor can send a value to one of its neighbors, and it can receive a value from one of its 4 neighbors. Okay, so this is distributed array processor. A more recent example, although this one is quite old too, of associative processors. Okay, this concludes my discussion of search acceleration circuit. This section dealing with VLSI trade-offs in search processors, basically when you implement large search processors, what are the VLSI considerations in terms of basically complexity of processors, their placement, connections between them, whether you need long wires or you can do it with short wires, and so on. This will eventually be discussed in this section once I've had a chance to write it. So that's it for today. Next time next lecture, I will cover chapters 8b and 8c. I will go rather quickly through them, and this will conclude, that lecture will conclude our discussion of part 8 of the textbook. Until then, please stay safe, and please contact me if you have any problems with the lecture or other aspects of the course. Okay, goodbye.